Thank you very much, Rodrigo, and nice to meet you all. Thank you for the nice introduction. Rodrigo, are you going to record the presentation?
Yes, we are recording all presentations.
Okay, thank you very much. So before talking about robotics and perception in agriculture, I want to show you a little bit about my university. I'm not so sure how many of you know my university. So Federico Santa Maria Technical University is the building that you see here, and it's just in front of the ocean. From my point of view, since I have worked in 4 countries already and several universities, it's one of the most beautiful universities here in South America, and you are welcome to visit us sometime when it is possible. So just a few pictures that I took of my university, and then we are going to discuss about robotics, which is the topic, you know. We have a center. The center is called AC3E, the Advanced Center for Electrical and Electronic Engineering, in which my entire research line is inserted. I am one of the PIs of the center. There are only a few centers in the country. Those are funded by our CONIS, our National Science Foundation. And well, my entire research line and group is in the center. We work not only for researching, but also for the industry. So we have several projects managing there, both for research and the industry as well. Just a little bit about our center. We have 6 research lines. We are working on renewable energy, data analytics, artificial intelligence, biomedical system, control and automation, electrical systems, and also robotics. The robotics part is the one that I am the PI. And our goal within the robotic research line is this specific goal, farm automation technologies. So we are really focused on generating solutions to the agricultural industry here in Chile, but not only for Chile, but also for the world. In this sense, my group was formerly based on 10 PhD students. One of them, this one here, is already a researcher at the Carnegie Mellon University. This one is my current postdoc. This one is a professor in another university here in Chile. This one is a professor in a university in Ecuador. This one is a researcher at the University of Lincoln in the UK. This one is a researcher at the University UC Davis in the USA. And the rest are my current PhDs. Hopefully this year I'm going to have new ones. The thing is that working on robotics and perception in agriculture somehow is attracting the attention of the rest of the world. I mean, the work we are doing here. A little bit about Chile. I'm sure that most of you know what is happening in Chile. We have the earthquakes, we have volcanoes, we have the constant hydric emergency, we have the lack of human labor force working on the field, and also our pharma field is not as is not planar. So most of our groves are on the slice of the mountains. We have onions, we have apples. We're kind of famous because of the apples, of course, of the grapes, especially the table grapes, but also the grapes that are used for wine. The blueberries, in the last decade, blueberries are like an emerging commodity. So they are really, for 1 hectare, you can produce more than 10 hectares of grapes. Olives and that's it. I mean, Chile in particular is what I like to think is a vertical country. You have Chile here, and Chile is entirely on the Andes Mountains. So we have to grow on the Andes Mountains. This is a huge challenge. And in particular, if you see what I have on the right, you will see that on the north part of Chile, we have the Atacama Desert. Right now, we cannot grow almost nothing there. In the south part, we have the Patagonia, which is, a protected area. And most of the growing happens here, between this region and this region. And we have everything there. It's like 1,000 kilometers plus minus 200 kilometers. And everything happens there. But you know that the widest part of Chile is about 100 kilometers only. So the actual farmable land that we have is really, really small compared with the rest of the countries. And another thing, we have the Andes Mountains on our east, but on our west, we have what is called the coastal mountain. So we have two mountains and a valley. And this is the only part which is farmable in Chile, if you cut Chile in the middle. So it is no more than 30 kilometers wide. So we have to, we have to grow everything there to feed our country and also to export our commodities. These are the main fruits that we export. We have pears, avocados, which are really, we are one of the top 5, actually number 5 exporters on avocados. We have cherries, kiwis, oranges, and grapes, blueberries, and etc. But in particular, table grapes, they are like the 50% of our DGP. If we compare how much our growings contribute to the DGP, then table grapes, they contribute 50%. So we have a lot of challenges here. We have our groves are on the slides of the mountains. We have hydric emergencies, and we have volcanoes, earthquakes, etc. So as any other country, we have to adapt technology to our own needs. Well, this is the scenario we have to face. So I'm going to talk right now about robotics and perception in what is the Chilean agriculture. My name is Fernando Auat, by the way. I'm associate professor in the Department of Electronic Engineering at University at Federico Santa Maria Technical University. Also, as Rodrigo said, I am associate editor of Computers and Electronics Engineering and associate editor of Biosystem Engineering, and also this other journal from the IEEE, Open Journal of Intelligent and Transportation Systems. If anything, and you have my contact here, if you can write me anytime. About phenotyping, what we have done, this is just a brief of what we have done. To give you an idea, I started to work in robotics in agriculture in Chile 10 years ago. I'm not Chilean, I'm from Argentina, another country. So when I arrived to Chile, I started to work in robotics and perception in agriculture in the Chilean scenario. So far, we have in Chile published more than 70 journal papers, Web of Science journal papers. This is just a brief of what we have done in the last 3 years. We have been working a lot in phenotyping. In this sense, for example, we build our own technology or integrate our technology with existing one. For example, we have here the SIG LiDAR, the ones that are used for mining, especially. And we have a tripod for, telescopes. So we integrated the LiDAR and the telescope, and we use it with a ROS operating system. And we started to measure, in this case, acquiring a cloud point of canopies and modeling the canopy. Then we started to work on some computational approaches for modeling the canopy. We started what this is widely known as voxels. So we started the voxelization process of canopies. And this is quite interesting because when you are phenotyping canopies, there are a few characteristics that are quite important. For example, what is called as porosity or penetration is the amount of sunlight that can penetrate the canopy. I mean, you have the sun over here and you have the light. How much light, how much light are reaching the ground? Is reaching the ground. So this is called penetration, and we can measure the penetration or the porosity of the canopy. Also, we can adapt the size of the voxel to the species which we are working, and also to the size of the leaf. So we can have a computational structure of the canopy quite accurate, and also we can measure, besides the porosity, we can measure the leaf area index, we can measure the volume of the canopy, and we can measure almost everything that we can model with the voxelization process. Then we started to work with almost the same procedures, but now we moved to, to analyze, because in this case, for example, in the previous presentation, we have the LiDAR, and the LiDAR is, acquiring cloud of points around the canopy. But the thing is that when working in agriculture, we are kind of dependent on the localization system. In robotic systems, which is our main topic, when working on robotics, localization is the first problem you have to solve. If you don't have a good localization system, then, nothing is going to work. So when we have an RTK, a real-time kinematics, or a GNSS antenna as a positioning system in our robot, there is one thing that we have to model, and it is the error. When you have a machinery applied to agriculture, and you design a machinery, and the localization system is one RTK that costs like $100,000, it's going to be really difficult to sell that machinery. So we analyzed which is the error that we have when phenotyping that is correlated to the error in the RTK. So we started to work with one very accurate RTK and to add error to the localization system, and then to see how that error propagates to all the characteristics that we are, extracting from the canopy. We did that with our colleagues. We work a lot with University of Lleida in Spain, also with the UC Davis, and also with the Washington State University when we are doing the field experiments. So we did that. And we started with the accuracy of our RTK that was around 1 centimeter when it's static. And then we started to add error. And one thing happened is that when we started to add error that was bigger than 1 meter, all the parameters started to converge. And when I say the parameters, I mean the surface of the canopy, that is kind of the leaf area index, the leaf area, the volume of the canopy, and also the porosity. So if you are, for example, this is only for deciding which RTK you are going to use as a localization system. If you buy one simple GNSS antenna that has at least 1 meter of error, it doesn't matter if you pay for 1 meter or you pay for 10 meters. The error that you are going to have is the same when you are estimating at least these 3 features from the canopy. This is quite interesting because it allows you to decide which fusion strategy are you going to use to make the localization system more accurate. Those are the articles that were the result of the analysis. Let's go to fruit detection. This is another topic. We have a robot. This is a robot, by the way. This is an automatic spraying system. We have the RTK here. Sorry for not explaining before. We have a LiDAR. Actually, we have LiDAR cameras and a lot of things. So we started to work with the reflectance from the LiDAR. It's not just the measurement, the range measurement, but also the intensity of the ray that returns from the impact. So we started to analyze and how to try to detect fruits in the grove. So we got very good results because fruits reflected the intensity differently from the leaves. And we were able actually to detect fruits much better than using only range measurements. Of course, you are going to say, why not using, for example, RGB cameras or anything else? Well, we started to fuse RGB cameras with 3D cameras, with LiDAR, with intensity, with thermal, etc., multispectral as well, and to try to find which were the best set of cameras that we could use for detecting fruits. So we have 4 reflectances. Using the LiDAR, we got very good results. And also using, of course, the RGB and RGBD cameras and so on. This is just a video because as many other research groups are working on, we are working also on deep learning techniques. We have this huge problem for many years that was detecting avocados. I don't know how much do you know about the avocado tree, but the avocado tree is kind of very complicated. The avocado grows almost in every part of the tree. The texture, the color, and everything of the fruit makes it so difficult to detect, because including that the fruit is within the canopy. You cannot see it most of the time from outside. So we started to work with deep learning techniques for detecting, for counting, but also for semantic segmentation. This is quite interesting because we are now able to follow the asset in the agricultural growth, and also to predict the actions of people working there. Because one thing that we did is that modeling the entire behavior of people working in this case, in the harvesting process, which is not, there are not infinite actions. There are just a set of actions. Those are a lot of actions, but they are not infinite actions. So we were able to model all the actions by semantic segmentations, and now we are able to predict. For example, if you are picking the avocado, then you are going to take the avocado to the bag, just to give you an example. So the actions are predictable, and we developed also, based on some calories metrics, a way to interact, minimizing the calories of the field worker. This is something that is still under review. But we were able to, this is a metric that we are using to measure the interaction of machinery with field workers. And we are using with robots, actually. The same that we did with avocados, we did with apples in California, and also with lemons here in Chile. And we are right now implementing. This is actually already implemented, but we are exploring other techniques for counting, because one thing is to detect. You have a lot of images or videos, and you detect the feature. In this case, the fruit. Then you have to count. And the problem is that you cannot have overcounting, because the idea is to have a precise yield estimation of the harvesting. So we also worked on techniques to track the fruits within the deep neural network that we are implementing with kind of good result. Those are published already in Computers and Electronics in Agriculture. We did the same for estimating the production of, in this case, berries in Talca region. I think is the 7th region in Chile. So we did the same. Those are the deep neural networks. Actually, those were recurrent neural networks for estimating the production. And we had an error of 8%. When compared with the error provided by the client, in this case, he said that they were having an error of 35% in estimating the amount of berries to be harvested. When we did the experiment, we had an error of 8%, which is a huge improvement. This is just a few images to depict how we work. We try to use cameras that are manually handled. That's why I said robotics and perception in agriculture. Because you know that when you propose a solution in agriculture, most of the times, those are going to be ad hoc solutions. So it's not like I'm going to sell to the farmer this high quality, very expensive camera. No, they want some solution that is good, that is cheap, and that could be scalable. They could take it from one farm to the other one. So we try to use the most commercial cameras that we can find here in Chile, or something that is actually simple. In the case, for example, of avocados or apples or the lemons, we used just our cell phones. Well, this is for berries, and as I said, we had an error of 8%, which is kind of good. Also, we were able to classify the kind of berries that were, we divided in 4 quartiles. Berries that were about to be harvested, the most mature ones, and the ones that should be discarded. So this is just one of the the metrics that we were using. As you said, as you see here in this table, at least, we are when we work on this kind of with this kind of techniques, we try to use the most amount of data that we could have. Another thing, and this is more about robotics, we are working on these end trailer systems because this is quite important. One robot doing everything is kind of, is like a dream. It's more science fictional, but we should be thinking about several robots doing something, and sharing the workspace with people. This is the next step. It's not like for tomorrow we're going to have a robot doing everything by itself. No, let's think gradually. So we have a robot and it's sharing the space with people. We're working with end trailer systems, in this case, sharing the space with people and sharing the work with people. For example, and this is more about the control systems, we are now studying how to maneuver end trailer systems between furrows, between alleys in a grove, without hitting the grove, actually. And one problem that we solved is how to park in reverse, because it's important to position the end trailer system when you are about to harvest. Of course, everything that we are doing here is only to collect the harvesting, and that's it. It's not like the robot has many manipulators and are touching. No, it's just a robot moving and collecting what is harvested, because we have to solve one problem at a time. And this is only for parking in reverse. This is tested for end trailers. That means it's not only 3. In the literature, you can find that stability is proved only for up to 3 trailers. But we were able to moving the join point between a trailer and another trailer, just moving the point, we were able to extend to end trailer system, and it is stable. And this is published also. So we are working on the maneuverability strategies to avoiding hitting the corridors. This is just some of the results that we have. We are testing. We tested actually here in the Valparaiso the number of trailers, the probability of impact, and how much space we are going to need to maneuver. And what happens if we have a person also? We have to be able to, to avoid. Actually, we try not to avoid the person. It's not like we're going to hit the person, but we're going to stop the system until the person is moving, because it's much more cheaper to stop the system, because this is electrical. This is, sorry to say, I forgot that. Now we're working with electrical engines and not combustion engines. So it's much cheaper to stop, wait for 1 minute or 2, expect the people to move, and then to continue our motion as robots. So these are some of the results. This is just to prove the stability. We are also working with model predictive control in this kind of things. What happened when we have trailers of different sizes and trailers of different nature? Also, this is part of our study. And we were able also to prove the stability, the scalability, and so on, maneuverability of these kind of systems. This is for the one that is actually on this topic. This is purely control and estimation theory. And if you want to see a little bit more, I'm putting below each slide the publication where the citation. So we solved the problem of maneuvering with end trailer systems with different kind of systems, and reducing also one specific thing, that is the energy consumption. And this is going to be my last topic, actually. This is just some statistics are important, because we are, this is for example, when we have 10 trailers, when we have 8 trailers, 6 trailers, 4 trailers, how the system behaves in the sense of heating. So we try to avoid hitting the grove and, of course, hitting people. We are also working with multi-end trailer systems. strategies for harvesting. This is purely simulation. This is purely simulation because the last year we were in the lockdown and we didn't have the space to do the experimentation. So this is purely simulation. We presented the framework that is already published, also a framework to manage N vehicles. Each one of them is an N trailer system for harvesting, where each harvesting point has its own schedule. Another thing that we are doing regards remote sensing. Valparaiso region, we have the 97.5% of our vegetation is only Pinus radiata and Eucalyptus globulus. And we have around 30 fires per year. So, it's kind of huge to try to detect when we are going to have a fire or which part of our region is going to be affected by the fire. So we are studying the moisture content, the water content of the leaves. So we started with an hyperspectral camera. This is a very, very expensive one. It has a resolution of 1 nanometer, and it goes from 350 to 2,500 nanometers. And we started to see in which part of the spectrum we had the information about the water. There are several well-known indices, the one that we have on the right on the screen, and they somehow refer to the water content. But the problem is that the camera that we used, it's about, again, $800,000. On an UAV, trying to measure everything is really expensive. So we started to study what would happen if we narrow the spectrum just to the part, and this is all the information theory, in which part of the spectrum we have the information that we need to estimate the water content, meaning to estimate all the 16 indices that you see here. So which part of the spectrum, where we have the information. It's not only checking the wavelengths that we have here. Let me try to reduce the explanation. You see here, for example, this is for the Pinus radiata and this is for the Eucalyptus globulus. And this is what happens when we are during the dehydratation process. We have an oven and we put the leaves there and we started to dehydrate and see what happens. But the thing is that cameras up to this wavelength are kind of cheap, but cameras up to this wavelength are really expensive. So the first thing that we did is to study what would happen if with this information that we have here, we can estimate what would happen with the spectrum on the other side. So this is one of the studies that we did. We did it and the results were, very accurate. We were able to predict the other 16 indices with an error of 88%, as far as I remember. This was also published, and that encourages us to go further. I'm going to move a little bit faster here. It's not only, let me go to the part that I want to explain. It's not only to work with 350 nanometers to 1,000 nanometers. It's just that in that interval, spectrum interval, we have information that is now needed. So, for example, let's go again to the previous spectrum that I showed. This one here. You can see that all the information that we have here is not, is not important. The information that we have here is not important. And perhaps the lower information that we have here is not important as well. So we started to study which are the key wavelengths that, is like extracting the poles from a system. Have the poles, have the zeros, and then we have the model. It's something like that. So we found out which are the key wavelengths, and actually are only two, that allowed us to predict the other 16 indices, with some error, of course. We're going to have errors. But it's more cheaper to have one camera or two cameras with one filter or two filters than having one hyperspectral cameras. And the results were really nice, actually. We were able to do that. We were able to predict. And this is, I just want to show you, we have a very good prediction of the 16 indices for up to 24 hours of dehydration of the leaves. This is just for remote sensing. And we are now working on what is called the probability of ignition, since we are able to measure and to estimate the amount of water on the leaves. Then we can say, for example, if there is a fire, this canopy is high, the probability of propagating the fire by this canopy is high or low, according to the amount of water. So this is about, I'm going to pass these slides, and these are the two, actually there are four already about this specific topic. And I think it's important because we are showing that we can estimate the amount of water on leaves just using a couple of wavelengths. Finally, about robotics, and this is one of the key things that I do. I work a lot on making vehicles more efficient from an energy point of view. In this case, this is robotics in the sense that when you propose, for example, a motion planner, and you have the controller and you prove that the controller is stable and is robust enough and etc. But the thing is that almost no attention is given to the amount of energy that, for example, the transient response needs. To give you an example, if you are on a vehicle, an autonomous vehicle, and you are at a cruise control of 100 kilometers per hour, and the vehicle is traversing over sand, pavement, grass, gravel, I don't know, any other kind of terrain. The thing is that as a rigid body, the vehicle is going to be traversing at 100 kilometers per hour. But the effort that the engine is doing to reach the cruise control is different if you are on a pavement or on grass, on gravel, sand, or any other kind of terrain. And this is because of the cohesion that you have between the wheel and the terrain, or the thermomechanics parameters between the wheel and the terrain. And also because of the tuning of your controller. I mean, the tuning, when you tune a controller, for example, you design a controller and you said, well, this is stable as long as these parameters are between this value and this other value. Just, I'm trivializing something. But I mean, between the lower bound and the upper bound, where your parameter can behave, you have infinite possibilities. And one of them, or a few of them, are going to optimize the amount of energy that you need to accomplish the reference. So this is part of my work. So we have an automated golf cart with all the sensors, and this is the one that we use for our experiments. Right now, we are working on what is called the IPC, the instantaneous power consumption. We are computing, estimating, and predicting the instantaneous power consumption for the route planning problem. That means if you have a route, then you can, and some information, of course, then you can have beforehand how much energy you might need to traverse that route. And that is really, it's not only a problem of urban vehicles, it's also a problem in agriculture because it's a lot of logistics that you have to handle. This is part of the electronics that we do. I mean, the modeling, because we are electronic engineers, by the way. And we integrate everything using the ROS operating system. This is almost our standard already. This is just some examples. We are using what we know in featuring or characterizing terrain, and we tried our system in different kind of terrain. This is our campus in Viña del Mar. This is another city. There I have 10 hectares where to prove my experiments, where to do the field trials. And we try it over grass, clay, pavement, gravel as well, etc. Some results of how the IPC behaves. There is a phenomenological model of the IPC, which is kind of well known, but depends on many other parameters that you have to model and estimate so many things that is a really complex stochastic process. So we started to model based on data. One thing is the IPC when you are accelerating, and the other thing is the IPC when you have cruise control. So these are the results that I want to show you. And I think I'm going to stop here because, Rodrigo, as far as I know, my time is over, right? This is what is important. In yellow, you have, you have the four kind of terrains here: clay, grass, gravel, and pavement. But in yellow, you have the estimation of the energy. In this case, yes, energy. It could be power as well. There is one derivative of difference. The energy according to the manufacturer. Then we have the energy measured directly from the batteries. This is, we have it in blue. And in green, we have the prediction of the energy and the energy predicted. So we tried several trials. You have there just an example of 10 trials. The manufacturer says that you are going to need, for example, here, this is here. Well, for example, here. You need this amount of energy for the test. According to our sensor, the sensors that I show you, well, basically here, this layout is for sensing and recording the IPC. According to our sensors, what you actually used of energy is what you have here. And according to our model, the model that we are building based on data, as I said, we have a model with constant velocity, the cruise control velocity, and then a model with acceleration for the four different terrains. So what we have is that our prediction that is here is closer to what we measure. And it is half, the amount of energy that the manufacturer is telling you that the vehicle is using. So the big thing here is that we can double the life, it's not the life, the duty cycle of the vehicle, disregarding what the manufacturer is saying. This is quite important because when you're harvesting, you need to plan a route. The idea, if the vehicle is without any energy, is going to be stopped just in the middle. In the case of combustion engines, you go with some fuel and that's it. But in the case of electrical vehicles, you have to charge the batteries. So having a very accurate way to predict the amount of energy is going to ensure you the accomplishment of the route. An example, and this is a video of what is happening actually. This is an onboard camera, and what you see on the right is just the way the vehicle recognizes the different kind of terrains. So what we are doing actually is we are recognizing the terrain. This is just driving the vehicle at the cruise control. But we are recognizing the terrain, and according to the terrain, we are setting the parameters of the PID controller, low-level PID controller that we have in the cruise velocity control. And in that way, we are able to make more efficient from an energy point of view. And also, we are there implementing the prediction that I said about the energy. The articles that we have are the ones, well, we have more, but those are the first articles that we have on the topic. And that's it. That is my presentation. This is my contact. If you want to contact me, feel free to write me. Also, if you want to find me in ResearchGate, in the IEEE Collaboratec, also my ID in Scopus, just in case. Thank you very much for your time. This is the work that I have been doing in the last 3 years here in Chile.